Okay, so today I'm going to present this paper, Intrinsic Flatter-Zella-Scully Theorem, which is available on the archive. And before we do that, I want to review the key points from the last meeting from Wednesday. So we talked already about how the intrinsic flat distance between two spaces, if I call this one M1 and X, M2, that this was an infimum of the flat distances inside Z's of the images of the currents. The infimum is over the Z's that are complete, and the phi i's from mi's to z's that are distance preserving. And that this infimum is actually achieved. So this is achieved. And Z could be actually it would be perfectly equivalent definition if we took Z to be one dimension higher than the spaces. And so let's make the spaces m-dimensional. So we can have Z as m plus 1 dimensional rectifiable. And or we could take Z-Banach. And that there was this Kuratowski embedding for going between them. And then as a separate, so those were theorems that we were able to do that. So it's the original definition is that it's complete, and then these are two facts that were proven that you could take the infimum in that class. Another theorem that we had was that if mi flat converge to m infinity precompact, this is also achieved on their precompact. Then we actually could find a common Z. There exists phi i's from mi's to z of the same classes, such that the flat distance in Z of the push forward goes to 0. This common, by putting them all into a common Z, this allows us to prove many theorems, so I want to be able to use this today. And using this theorem, we had said that if we had another theorem which said that if mig to x, then a subsequence of the mi's flat converge to an m infinity, which is contained inside x. Right? So that was proven by the fact that when you have a Gromov-Hausdorff limit, you can put them into a common compact Z, and then you applied, that's Gromov's theorem, and then you apply Ambrosio-Kirchheim. Sorry, I need to say one more thing. I'm being too quick here. And mass. Mi, boundary Mi. Beautiful. We need bounded masses and the boundary masses, okay? So if you have that combination, that they then have a flat limit there. All right, and then the last thing I want to review is that notice from this theorem that if the GH limit is lower dimensional, then the flat limit is the zero space. Okay? And when you have the zero space, you treat this definition as being infimum over, you don't need, if this one's 0, 0, 0, you don't actually need a distance-preserving map for the second one. You just take comparison this guy to 0. So this is all fine. So that's saying that whenever you're collapsing, intrinsic flat limits are not useful as a method or a tool. And then an important question is, when does the GH equal the flat limit? And there's many results in that, which I'll mention today. Okay. All right, so that's just a review. Any questions? This is sort of a smattering of theorems that I'm going to need to refer to today. Got a little confusing here. Okay? All right. All right, so what we want to understand is when are points converging and when are points disappearing. So we need to discuss disappearing points. So let's just make this, I'm going to star this. I'm going to add that there exists Z. Put a star in this equation. Okay. So definition, a sequence of points pi in xi is disappearing. Let me not say disappearing, let me be very precise. Has no limit in x bar infinity, the symmetric completion. If, when you do this process, if when phi I taking xi to z has phi I p, satisfying star, that's why I said star there, satisfying star. So when you put them into the common space and you take the limit, then phi I pi, which you can think of as a point zi in z, converges z infinity, which is not in phi infinity x bar infinity. So that would be a notion of saying that point is disappearing. So after you've put them in there, yes, the points converge to something, but they're not actually converging to something that's in the sequence of spaces. So picture something like this. Q1, Q2. Intrinsic flat limit is this, but sort of z infinity is over here, if you want to think of it that way, right? But this is phi infinity, x bar infinity. So there's this. Yeah, now the Gromov-Hausdorff limit includes z infinity, but not the intrinsic flat limit. Okay. So we wanted these spikes to disappear for the applications of non-negative scalar curvature in order to have compactness theorems, but now we want to know which points are disappearing because that's useful to be able to understand. And we say pi in xi has pi converging to p infinity in x bar infinity if there exists phi i's from xi's to zi's satisfying star such that phi I pi converges to phi infinity p infinity. And that matches exactly the notion from Gromov-Hausdorff convergence, where you would say that points in the sequence converge to a point in the limit if you could set up these maps like this. However, the big difference between Gromov-Hausdorff and intrinsic flat is that in Gromov-Hausdorff, the limit spaces are already completed, so you don't have to worry about taking the completion. And in Gromov-Hausdorff convergence, nothing disappears. Okay, so nothing disappears, nothing has no limit in the Gromov-Hausdorff case. So the PIs for the second definition, these PIs will be here. The terminology's been on the archive for a year, but this notion is exactly matching Gromov-Hausdorff. No limit in x bar infinity is being clear because there's also the possibility of saying there's no limit in x infinity, which is slightly different, of course. And there are different theorems for the two. That's why I said it. So they're disappearing in two different kinds of ways. And that's why I wrote it precisely that way. So a very basic lemma is that for all x in x bar infinity, there exists xi's in xi such that xi go to x infinity. So for every limit point, you can find the sequence that is approaching it. Okay, so in that sense, this is the same as Gromov-Hausdorff. Okay, so the proof is that you take your maps phi I, so we take z and phi I satisfying star. And you have your sequence. So let me just draw a sequence that here's our M infinity, M1, M2, and they're flat converging here. And then we take them all over, phi 1, phi 2. When you move them over here, they start to overlap, right, inside Z. So they're very close to each other. The last one is here. So your last space, this one, has been mapped to here. And now you take your x here, and you make a ball around this x. So this is phi of x. So you look at the ball about phi of x of radius epsilon inside Z. And over here, we have the phi 1 number, the push forwards of each one of these guys as currents. So I've drawn their sets, right? So this is phi 1 number T1, phi 2 number T2, and then finally phi infinity number T infinity. And because phi x is actually inside, since phi x is in the set of phi number T infinity, that's what's given. We're assuming that his, actually, the support, because it's completion. It's symmetric completion, so the closure of the set, okay? The support of this guy. So he's sitting in the yellow set that I shaded here. Because since he's there, then this means that phi number T infinity, phi infinity number T infinity, restricted to B phi x epsilon is not the 0. Right? Okay, not a problem. But then Ambrosio-Kirchheim showed, but AK showed that phi I number Ti restrict the same ball converges 2 by infinity number T infinity restricted ball. Now we need to take almost every epsilon here, and here we need to take a subsequence. Okay, so you have that for almost every epsilon, and we have a subsequence here, but that's all right because we're only trying to understand the limit here. So we have these phi I number Ti's doing this, and then we say, well, if they're converging to that, which is not 0, then none of these guys can be 0. So these guys are eventually not 0. Actually, let me do weak convergence, and then we don't need a subsequence. Then this guy's not, so eventually these guys are not equal to 0. So if they're eventually not 0, so there exists the xi's in those sets, Ti's, that are ending up in this ball. So we have these xi's here going there. And then we take some diagonal argument in epsilon to 0. The proof in the Gromov-Hausdorff sense is similar. When you have a Gromov-Hausdorff limit, you'd say take any x here. Well, the Gromov-Hausdorff distance between this and one of those previous levels is in tubular neighborhoods means that there must have been some guy nearby. And it's fine. It takes a little more work to do this with intrinsic flat convergence because of this issue of having to restrict to balls and get the weak convergence and then go back. So it takes just a little more argument. It's quicker in the Gromov-Hausdorff case. Okay, so that's a standard lemma. You can just use it now. And without much more effort, you can say that if x and y are in x bar infinity, there exists xi and yi's in xi such that xi goes to x, yi goes to y, and the distance between xi and yi converges to the distance between x, y. So the lim inf as I goes to infinity of the diameter of xi is bigger or equal to the diameter of x infinity. Okay, to prove this is pretty much exactly the same proof as here, except we also keep track of a phi y, and we get the yi's going there. And since the distance, these are distance preserving maps, the distance between these guys is the same as the ones from earlier. So this is fine. This, in the Gromov-Hausdorff case, you can then prove that the limit of the diameters is the diameter because the sequence of points has a converging subsequence. But we do not have that this is definitely can drop. So keep in mind, this is not a limit. That particular example there, if you look at those pairs of points there, you can see that in the limit, the white sequence of points has no limit. The diameter dropped in that sequence. Okay? All right, so that's a distinction with Gromov-Hausdorff. All right, so now what can we say about points that are actually disappearing? If I have a sequence of points that actually disappears, if pi has no limit in x bar infinity, then there exists a radius greater than 0 such that the flat limit of SPIR 0 equals 0, where, let me say, I have to do the almost every. Let's make this a capital R. almost every little r less than capital R. This is like geometric math. We always have to have our almost everys, right? Where almost every little r bigger than the r, the flat distance SPR IR to 0 is 0, where SPIR is an integral current space that's created by taking BPIR closure, distance I, and TI restrict BPIR. So these are balls viewed as integral current spaces. So you think of it as an integral current space itself, you call it SPIR, and then it's the ball, the restricted distance from the whole space. So this is saying if there is no limit at next bar infinity, then there exists some r such that eventually these guys are disappearing. So the picture should be similar to this picture, but now we're going to follow these tips, okay? So I want to look at the tips in the proof. The flat distance is going to 0, sorry. Thank you so much. This is converging to 0. It may not ever, it's converging to 0. So the proof of this, I just want to, let's look at these PIs, the purple PIs, right? So you're studying these guys at some tip, P1, P2, and they're going nowhere. So the image is P1, P2. This is, sorry, I1, P1, I2, P2. And it has maybe some limit Z infinity here, but it's not actually in there. So now you take, since this is a closed set here, x bar infinity, this is closed, you can take a small radius here that avoids. You choose your r so that B, Z infinity, R intersect phi infinity, x infinity bar is an empty set. And then you argue that none of these guys eventually, then you do the same thing here, where you look at, oh, well, what is, so then phi infinity, T infinity of this guy, replacing him now with Z infinity, right? So this guy is 0, opposite, right? And then you say, well, this guy has to converge. So but this guy's not 0, he is 0. So that makes the flat convergence to 0. Okay? It's actually only an integral current for almost every r. Remember, the boundary has to have finite. In a manifold, you don't need the almost every r, but in integral current space in general, a level set of a sphere could have infinite mass. And then the last lemma in this family of lemmas is about how we would like these balls to converge to limit balls. And so it's a slightly funny statement here, but if pi goes to p infinity, which is lying in x bar infinity, then there exists a subsequence such that for almost every r S P I R flat converges to SP infinity R. All right. The key problem with trying to prove that lemma will need me to draw a new picture, so I'm going to erase this picture. So if you want, to ask a question about this picture, ask now. Otherwise, I'm going to erase it. Okay? I'll erase it. So I want to give you the proof of this lemma, but this is getting too crowded to do it on top of the same picture. All right, so we want to look at this lemma now. Almost every R after checking the subsequence. Annoyingly, this lemma actually takes a few pages to prove, just because it's highly technical, all right? But the idea is, again, you have your, so let's just draw the pictures. Fi number Ti's are inside Z. So we'll just draw the part that's inside Z. So here's that one, right? And then we compare to F infinity number T infinity. And we have this guy here. And maybe this guy has a thin tube, right? Okay, and they're sitting inside Z that we're focused on. And we have our P infinity here. And we have our Pi, sorry. I have to push forward. P infinity. And we have our Di, Pi. And now we would like to take a pretty big R, so let's just take R like this big. Okay, so I'm only drawing the balls, sort of, in this picture. All right, so we have these two balls, and we want to compare them. The phi I, Pi, and the phi infinity, P infinity are very, very close, right? We have the distance inside Z between these two guys is very small. We know things like what we just were doing estimates on, where we could compare the ball around here with the intersection over there. So we could estimate things like D flat inside Z, phi j number, Tj restricted to the ball about P, phi infinity, P infinity, a radius R, contrasted with phi infinity number, T infinity, restricted to be phi infinity, P infinity, a radius R. Controlling this would be easy, because we have this lemmas that we were using to prove the last two lemmas that say that Ambrosio-Kirchheim say if you fix your point in the Z, you have the restrictions to the fixed point will be converging. So this one you can control. Because this set and this set are the same set. Okay? So when P, phi infinity, P infinity R is fixed inside Z. But we need to compare where this one is the J to the infinity. So that's difficult. Changing balls. So in order to study changing balls, what you end up being concerned about is you have this one ball here, and you have another ball. There was a picture like this earlier in this week, right? You have to compare these two balls that are slightly overlapped, which means you really need to control this mass here and here in order to compare changing balls. I'm not going to write out all the formulas because we'll just take the whole rest of the lesson. But you have two different center points. You need to compare a flat distance between two balls with different centers in the same current. All right? So these two are both in the same current. Say they're both in this TJ current with two different centers. Okay, so we have two different centers, and we need to compare this. We want to understand what is the mass of this kind of a set. And this would be less than the mass of an annulus region so we need to control masses of annuli. Well, the fact is you're not going to be able to uniformly control the masses of the annuli. That's actually impossible. So we will not be able to control the mass of these annular regions for the sequence PJs. And for this reason, we need to take the subsequence. So in order to control this, we'll need the subsequence. What you want to picture is this concept that happens a lot. If you talk about a sequence of functions which is converging to 0 in the L1 sense, what happens? You have possibility of first function like this, second function like this, third function like this, fourth function like this, so on, right? And in order to get them to converge pointwise, you need to take the subsequence to avoid the constant bumps. So if we want to control, there's a difference between controlling the whole volume underneath a curve and controlling annular regions. And because of this difference, it's the same kind of examples from functions which converge in the L1 sense to 0. The same problem is happening here, and that's why we need the subsequence. All right, so this lemma, I can't possibly write up the whole proof right now. I'm just trying to emphasize why there has to be a subsequence done here. And we construct examples of sequences and manifolds that actually need the subsequence in order to get this. They do not converge without a subsequence, based on these classical examples with the L1 convergence. All right. Someone tall or moderate height. I know. So I think we've had enough lemmas. It's time to have some theorems. All right, any questions? Fine. All right, so I said one of the themes that we were interested in is the relationship between intrinsic flat and Gromov-Hausdorff convergence. And we're already seeing here with the lemmas that we're able to prove that in some sense we're kind of able to prove half of what is true for Gromov-Hausdorff. That if you have a limit, then you have a sequence going there. Or the balls will converge to the balls, but with a subsequence now. Instead of in the Gromov-Hausdorff case, you would just have the sequence of balls converging and things like this. And so there is now the theorem, which I call the flat to GH theorem. Okay, so this is, you're going to start with flat convergence, and you're going to end up with a subset that has Gromov-Hausdorff convergence. So if mi's converge to m infinity in the flat sense, and m infinity is pre-compact and not equal to 0, then there exists SIs, which are integral currents. So these are m-dimensional, and he's an m-dimensional integral current in xi bar, right? Integral currents have to be in complete sets. So the mi's is xi di, right? So there's these SIs, which are m-integral currents in xr, such that if I create an integral current space, Ni, which is equal to the set of SI di from the mi's originally SI. So these guys are sitting inside mi. They're nice, rectifiable things within the mi's. Those guys converge Ni GH to m infinity bar. And the limit of the masses so let me draw what this means. You've got, say, your sequence is M1, M2. Here's your m infinity, right? And now I'm constructing Ni's, which will be Gromov-Hausdorff close to m infinity. So actually, the Ni's don't go down the tube. This can also be done even if there was no Gromov-Hausdorff limit, right? The Gromov-Hausdorff limit of this particular picture I drew does exist, it just has a line segment. But now suppose we do the one with increasingly many spikes, right? So if we have lots of spikes, then these ends cut off all of these guys. Ends only this spherical part of this picture, so you can always construct these ends that are nice, that have the Gromov-Hausdorff limit, and you can make sure you get the masses to decrease. So then the nice thing is you know the Ni's exist. Now you can use Gromov-Hausdorff convergence theory to say lots of things about them, and at the same time we haven't lost the lower semi-continuity of mass. So that's a useful fact. The proof is basically an implementation of Ambrosio-Kirchheim's slicing theorem. After we move them over to the Z, we slice, and we have to diagonalize carefully. So it's a long proof, I won't do it. But you basically take the distance function from the image of this guy, and you have to very carefully diagonalize and control what you're slicing these guys with the distance function from this guy. All right. And the first Arzello-Scully theorem time do I have? 20 minutes, right? Yeah, okay. So you fix some lambda greater than 0, and you have the mi m intrinsic flat converging to m infinity m, who's pre-compact. And you have fi's, which go from mi m to w, where w is a compact metric space. And that the Lipschitz fi's are all less than or equal lambda, then a subsequence converges and f infinity goes from m infinity m to w, and Lipschitz f infinity is less than or equal to lambda. And what I mean by a subsequence converging here is that if pi converges to p infinity, then fi pi converges to f infinity p infinity. It's the same as in Gromov-Hausdorff convergence. That's what this means. So in Gromov-Hausdorff convergence, if you have a sequence of manifolds that Gromov-Hausdorff converge to a limit manifold, and you have these conditions and a subsequence converges, Gromov proved this very early on. And very nice situation in Gromov-Hausdorff convergence is that the w's could also be changing. So in the Gromov-Hausdorff convergence, you get the exact same theorem, even with the wi's converging to w infinity. Your fi's go from mi's to wi's. The mi's, gh to m infinity. The wi's, gh to w infinity. And you get, and the Lipschitz bound, lip fi, less than or equal to lambda implies exists f infinity. From m infinity to w infinity. And all this guy has to be compact. Okay, but any Gromov-Hausdorff convergence are always compact. So this theorem is not true for flat convergence. We absolutely cannot change the w infinities in our case. Example, why in flat case we cannot take wi flat converging to w infinity, even if the mi's are fixed, are all 0, 1. And the image is the one that I drew in the beginning. You have this guy, and then a thin one. And the flat limit is two separate spheres. So if this is W1, W2, W infinity, then the fi's could be maps from 0, 1. The first one is this. The second one is this. Then there's no limit. So if the fi is taking an interval into the sequence, there is no limit curve. And this is crucial in Gromov-Hausdorff convergence that indeed this Arzello-Ascoli theorem does work with the w's changing, and it's used to get that the limit spaces are geodesic and have lots of nice properties. So we cannot make the target space change. Open question. What if the wi is gh to w infinity? So flat convergence of domains, gh convergence of targets. That might be true. So that's a all right, so that's one of the Arzello-Ascoli theorems. There's another one that's about isometries, where we do allow the w's to change, but the maps have to be isometries, local isometries, with a uniform bound on the local isometry. So they're exactly isometries on balls of a definite radius. So there is another, we do have a version that allows local isometries. Switch to white. Now we could allow the MIs, WIs, same dimensions, flat convert FIs, the maps, and FI are isometries. And by isometries, I mean one-to-one onto projective, okay, between on balls of fixed radius. These guys flat converge to M infinity. These guys flat converge W infinity. Then there exists F infinity, F infinity, M infinity, W infinity. Which is a local isometry. This local isometry condition guarantees that whenever the points disappear on this side, they're also disappearing over here. Okay? So you use those lemmas above. When they're not disappearing, we've got the flat convergence of the balls. Like here, this lemma star. We've got our balls converging in the flat sense on both sides. And they're isometries, so there's still isometries in the limit. And if there's a sequence of points that is disappearing, then both sides go to 0. So this is proven using those two lemmas. Exactly the same points disappear. This is applied in work with Sarah. To study limits of covering maps. Right? So when you're looking at universal covers or covering spaces, you have all these local isometries. And when early work of mine with Gofeng Wei, we had shown that the universal covers of Gromov-Hausdorff limits with Ricci lower bounds exist. And the way we proved it was by studying things with isometries of fixed radius. This theorem is already known to be true for Gromov-Hausdorff convergence, and the isometries will be on the same radius. And so if the radius went to 0, this would not be a local isometry in the limit in the Gromov-Hausdorff case either. And so that allows you to control covering spaces and try to prove topological results about the limits. So this was a natural theorem to want to prove in order to study covering spaces. And so Zera, this started some work on this. There's actually lots of very strange issues happening with the covering spaces. And this Harzel-Scully theorem I mentioned last time has been used for the non-negative scalar curvature questions to try to set up an isometry on the limits. All right, someone maybe quite, okay, you can do it. I had thrown it as far up. Yes, good, good, good. Now we won't need these lemmas, I can erase them. Oh, we're sort of hard. So basically, all these theorems are in one paper because they all use the exact same lemmas to prove them. Okay, so now for a Bolzano-Weierstrass theorem. So in a Gromov-Hausdorff convergence, if you have mi is gh to m infinity, Gromov said that they all embed into a common compact metric space. So then when you take the points over to the other side, their images are in a compact space, the subsequence converges. So if pi is in mi, then a subsequence converges to p infinity and m infinity. And this is not true in flat convergence. For two reasons. One reason that it's not true is because the z is complete, not compact. So that's already one problem. We're not going over to a compact Z. In the Gromov-Hausdorff case, you put them all into compact Z, then you use classical Bolzano-Weierstrass. So in Gromov's work, he refers to this just as Bolzano-Weierstrass because that's what he's doing. He's in a compact Z. But to make the same kind of theorem true with intrinsic flat convergence, we don't have a compact Z that we're going into. That's one reason. And the other reason is the points can disappear. Disappear even if the phi IPIs have a limit. So even if you manage to show they have a limit, they might not be in the limit space. So we have this double problem going on here. So what we do have is that the theorem says we need to somehow avoid the points disappearing. And in the process of avoiding the points disappearing, we actually luckily managed to show the deal with the fact that this wasn't compact, which is kind of a fun side effect. So we end up only needing to show the points don't disappear. So let me just write the exact statement. Where do I write this here? Yes. If mi flat to m infinity and there exists r naught greater than 0 and the function h, which goes from 0 r naught, oh, actually this is not including 0, 0 r naught to 0 r naught, such that if mi and pi are in mi, right? In Bolzano-Weierstrass theorem is supposed to start with the sequence of points, right? So you're given your pi's and you're given your mi's. And if there's an r naught and an h such that the flat distance of SPI r, that's the integral current space defined using the balls of radius r, right? to 0 space is greater than h of r for almost every r. All right, so we're saying there's a uniform bound on how far these guys are from 0. So that means we already knew from a lemma, that means that they're not disappearing. Because if they were disappearing, these would go to 0. All right? So just this condition alone avoids the disappearing. What's interesting is it also gets the subsequence to converge. Then there exists a subsequence, Pi going to P infinity and M infinity. So sort of magically, in the act of trying to prevent disappearance, we also managed to get the subsequence converging. Oh, this is in M bar infinity. All right, the reason that this is about M bar infinity is because when we had the lemma that used to be here that said that if you had a sequence of points that didn't land in M bar infinity, there was no limit in M bar infinity, this flat distance went to 0. For M infinity itself, guaranteeing P infinity is N infinity, we need stronger conditions. Nah, I just needed a uniform positive function. It just needs to be the same function for all the i's. This sequence that develops a cusp satisfies the conditions of the sequence. And this would be P1, P2. There's no P infinity in M infinity. But there is P infinity in the closure. All right? So the development of a cusp is allowed with these HRs. So the stronger hypotheses, theorems about P infinity actually in M infinity appear in joint work with Portuguese. It's on the archive already. It's called Properties of Intrinsic Flat Convergence. This paper is, we're actually adding to it before we submit it anywhere, but we already have the corresponding Rosella-Scully theorem on that paper already. They need Gromov filling. So it would really take an entire extra lesson to deal with them. You need this Gromov filling volumes to really control it precisely and strongly enough to guarantee things have this density large. However, even if you can't control filling volumes, which are very difficult to control, controlling this is not hard at all. This is just saying, I happen to know these guys are maybe converging in a Lipschitz sense somewhere. Or maybe they have those nice, we could use the work with Sajjad-Lakhzian, where we say that the regions in them are close to something, like diffeomorphics or something. So getting this condition to hold is not difficult. And so this theorem has been applied in a number of settings without needing to use the fancy Gromov filling. And what you do is you still want to know what M infinity bar looks like. What you do is you find out, M infinity versus M infinity bar, is you figure out what M infinity bar is using this theorem, and then you check the density afterwards. And say, okay, just take the points out that are not strong density. That's an easier approach than trying to control filling volumes. One last board, and just want to give a quick list of applications and then done. Well, this needs to be wet. So we can use this Bolzano-Weierstrass theorem to prove when Gromov and flat convergence agree. If you want to prove theorems of that sort, you can either use the Portuguese version, with Gromov filling, either use the Gromov filling version, or use the version here, use theorem, the BW theorem. And what you do is you take your, you have your Mi flat converting to some M infinity, and now you take, and you have its Gromov-Hausdorff converging to some X infinity. And then you take any point X in X infinity, then we know there exists Xi's and the Mi's. The Xi's go to X infinity. And then we show that there's S, Xi, R's, the balls, right, are good enough so that Xi's have a limit in M bar. And that limit would have to agree. It must agree with X infinity. So the goal is basically to control balls in the sequence. And so let me just do one last board, tell you who's used that technique. One reason that you want to show Gromov and flat limits agree is to show that Gromov-Hausdorff limits are rectifiable and haven't collapsed. So with the non-negative Ricci curvature without boundary, Cheeger and Colding proved that the limits were already, if they didn't collapse, they were already nice and rectifiable. But the boundary case had not been known yet. Oh, I have to squeegee this, sorry. So, with finger, CDPE, we had MIM with Ricci greater than 0, volume MI greater than equal to V naught greater than 0 implies MI M infinity equals X infinity. Okay? And these guys have no boundary. Okay, so that's the earliest one of this kind of theorem, that we show that the flat limit and the Gromov-Hausdorff limit agree. Okay, and then there's a theorem. This was put together without those lemmas, but sort of using those lemmas in a vague, kind of way. There's a theorem of Lee and Perales. Raquel's right here. Perales, which says that boundary MI equal empty sets. These are Riemannian. These are not. These are integral current spaces. With weight 1. So we're not going to allow doubling. The weights, remember they have integer weight. Satisfying Alexandrov found below. Alexandrov curvature gradient equal to 0. That's a triangle comparison. Then M infinity equals also the volume, right? Volume. Then M infinity is X infinity. And did we need a completion here? No, right? Right. So this one is proven by using the one where you first get that M infinity is the completion. And then, so the completion of M infinity is X infinity, and then you do density argument to show that actually every point was included. So the Alexandrov case has been done. RCD has not been done. CD has not been done. Okay? Perales in progress, very soon to appear. Are various Riemannian ones with boundary. And Ricci greater than or equal to 0. So she has to put conditions on the boundary. And again, that one's also proven by controlling the balls really, really well, and then later showing that the density is good. Okay, I'm done. Okay. Let me just write open. CD. So you guys know what your task is.